In this video then, I'll be going through the second half of the Breadth in Chemistry 2021 paper. So this is section B, the multiple choice section is in the previous video. So I'll be going through all the questions here, explaining how to answer them. I will spend more time on some questions than others, so questions that are based on essentially recall of knowledge and definitions, I will tend to skip over quite quickly because it is knowledge that you simply need to learn. It's not something you can work out in an exam. If you don't know it, you simply have to go back and learn it. So we'll go straight into it then with question 21 on the paper following the multiple choice. So atomic structure, number of electrons. This is very, very straightforward if you can remember the number of electrons. However, this is essential knowledge for A-level chemistry. So first shell of electrons then, this is what you learn at GCSE. You have 2 electrons in the first shell, hydrogen, helium. In the second shell, you have lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. There's 8 elements there. So you have a periodic table in the exam, so you may as well use it. So you get 8 in the second shell, and in the third shell, you include this D subshell, which is where the transition metals lie. So you have an extra 10 electrons present, so there are 18 electrons. In terms of how these are categorized then, the number of electrons in the S subshell is always 2. Doesn't change. Of course, the first shell only contains one S2, so we stop there. The second shell contains 2 S2 and 2 P6. And then the third shell is 3 S2, 3 P6, 3 D10. Okay, so the numbers in these columns don't ever change. Okay, so the S subshell will only ever contain 2 electrons. The P subshell will only contain 6. The D will always contain 10. Okay, the shell totals will differ as you add new subshells to it. But again, this is something you absolutely must know. Okay, so in terms of the marks for this, if you get the first 2 rows correct, you get 1 mark, and the third row correct is the second mark. Okay, so mark by row. Okay, so selenium, atomic number 34, and it gives you 2 isotopes of selenium with a mass of 76 and 82. Complete the table to show the number of protons, neutrons, electrons. Again, very, very straightforward question. So it's like a GCSE question. So remember then, the atomic number is the number of protons and electrons for an uncharged species. So that means that protons and electrons are 34 here and here. The neutrons you simply work out by taking the mass number, okay, so in this case 76 and 82, and subtracting the number of electrons. So for selenium 76, you'll have 42 neutrons, and for selenium 82, you will have 48 neutrons. Don't use your periodic table for this, okay, because on your periodic table it gives you selenium with a mass of 79. That's not part of the question. They've given you the information to use. Make sure you use it. So relative atomic mass then, straightforward calculation. You'll be surprised on the breadth papers. It seems like a very common theme. It is a common theme. On the breadth papers, practically every first question is an atomic structure question, so this is no surprise here. Relative atomic mass from a mass spectrum then. So here's a mass spectrum of sulfur. Calculate the relative atomic mass. This is nice and straightforward. So in order to make this work, so you've got different percentage abundances. So therefore, to make this work, we need to find essentially 94.93% of 32, 0.78% of 33, 4.29% of 34, and add them all together. Now, there's varying ways of doing this. I mean, there's 2 ways to do it. You can do 32 times 94.93, 33 times 0.78, and 34 times 4.29, then divide everything by 100. I don't do that because I just divide the abundances by 100 to make it easier. So there's multiple ways to do this, but effectively you're doing 94.93% of 32 and so on and so on. So to do that, we'll just quickly run through it for 2 marks. So 0.9493 times 32. Add that to 0.0078 times 33. Just be careful when you convert the percentages. You've got to divide 0.78 by 100. And 0.0429 times 34. Add that all together and you should should get a 32.0936. So once you've got 32.0936, again, just read the question. It's a bit of exam technique for you now, okay? I say exam technique, it's common sense really, but read the question. If it tells you 3 decimal places, give your answer to 3 decimal places. You're throwing away a mark if you don't do that. So you should get 32.094 as the 6 rounds up to the 4. Okay, and you get 2 marks. Nice and straightforward. Right. So different idea than this. Halothane, C2HBrClF3, seems very, very weird. General anesthetic in medicine, systematic name, a very long name here, 2-bromo, 2-chloro, 1,1,1-trifluoroethane. Draw it. So this is just challenging your ability to draw an unfamiliar compound. However, it is very straightforward because this ethane bit is lovely because it just means you've got 2 carbons in a row. And you've only got 2 carbons, so the numbers now make perfect sense. So on the first carbon, it's trifluoro, so 3 fluorines. And then we need to put a bromo on it, a bromine on it, and a chlorine on. And then the last thing I'm missing is the hydrogen. So there you go. So nice, straightforward halothane. They're just giving you a weird compound there to try and throw you off. So number of fluorine atoms then in 7.896 grams of halothane. So couple of things here. If ever you're asked about atoms, they put it in bold for you to begin with. This should be screaming at you Avogadro. Okay. But there's 2 steps to calculating this. Okay. So it's not as straightforward as it looks. First thing you need to do is convert grams into moles. Okay. Avogadro's number is useless without moles. So the first thing you have to do is work out the moles. Now, luckily, we've got the mass, we've got the molecular formula. So number of moles is mass over molar mass. And therefore 7.896 over the molar mass, which is 197.4, which they give you in the question, gives you 0.04 moles. Now, to work out the number of atoms of fluorine in halothane, then we first need to work out how many molecules of halothane we have. So we're going to do 0.04 multiplied by the Avogadro number, so 6.0222 times 10 to the 23. Put a decimal point there, I missed that out. However, this is the bit where people will get it wrong. Okay, you'll get 1 mark for getting the number of moles, but the next step is the hard bit, because if you multiply by Avogadro, what you're working out is the number of molecules of halothane. However, every single molecule of halothane contains 3 fluorine atoms. Therefore, you need to multiply your answer to this by 3 to work out the number of fluorine atoms in the compound. Think of it as though you were working out the number of, the number of arms in a room. Okay, you count the number of people. Let's say there's 20 people in the room. Sure, that's great. You know the number of people. But if you want to know the number of arms, you would then have to multiply by 2, assuming everyone in the room has 2 arms. Okay, so that would be, this is the same argument. Okay, if I just multiply 0.04 by the Avogadro number, I'm working out the number of moles of this. It's not the number of molecules. That tells me how many of these I have. The question wants the number of fluorine atoms specifically, and every one of these contains 1, 2, 3 fluorine atoms. So you got to times by 3 to get your final answer, and you should get 7.224 times 10 to the 22. You don't need to round this, okay? You can just leave it as it is because they don't ask you for any significant figures or decimal places. Okay, so enthalpy change is next then. So we've got an equilibrium given to us. We've got a delta H. It tells you here, so let's just do a bit of simple highlighting here. So rate of reaction increases when a catalyst is present. Complete the diagram below. So label the act. So again, I'm going to highlight these just to highlight. This is what we need to tick off. This is where the marks are. Okay, so we need to complete the enthalpy profile diagram. Label the activation energies. Label the enthalpy change of reaction. Now, first things first. Delta H, really important thing here. it tells us in the question delta H is plus 206. A positive delta H means an endothermic reaction. An endothermic reaction means that my products line has to be higher than the reactants line. That's the first common marking error. Okay, that's the first mistake people will make, is putting this line lower. Okay, it gives you delta H, it tells you it's endothermic, so make sure it's higher. Next, we just connect them up. So, oh no, that's terrible. I'm just going to redo that. Yeah, freehand drawing this is not my style on a graphics tablet. So up we go. Ignore my terrible lines. So that's the original energy. If we want to work out, so what do we need to label? Label the activation energies with and without a catalyst. So if you've got a catalyst present, you're going to need a second line. I'll do this in a different color in a minute, but for the time being, let's do it in blue. So just bring it across. Okay, just to be clear on this as well, we should obviously label our product line with 3H2 gas plus CO gas. Again, please make sure you label. You don't just write products. You're given the products. If you're not going to label it, you're just being lazy. Okay, you run the risk of losing marks. We'll put on our activation energy. So that line comes from the reactant line. It goes straight line, by the way. I've not got a ruler, so I apologize. Straight to the top, one-headed arrow that touches the highest point of the curve or somewhere close to that. It doesn't have to be perfect, but it should be as close to the highest point as possible. And this is EA, activation energy. Then it asks us to put one on with a catalyst. So with a catalyst, I'll do it in a different color just to show you this. You haven't got to do it in a different color in the real thing, obviously. You should do it in black, but the catalyst will lower the activation energy. So you need a second line that has a lower activation energy. I'm just going to do that one. And then draw a second activation energy from the same position you started to the highest point of that line and label that EC. Okay, so that's the two that you need. The only other thing, so that's that done that. Label the enthalpy change of reaction delta H. We can do that nice and easy. Let's just get the third color because let's get a third color. Let's just get green, why not? Now delta H starts from the reactant line, goes to the product line. So we start here and it should be a straight line again. I apologize. Now, importantly, for an endothermic reaction, okay, and for all reactions, okay, the reactant line goes to the product line. So the arrowhead must be at the top, not the bottom. It is not double-headed either. Okay, if this were an exothermic reaction, the line would go down and the arrow would be the other way. However, it is not. So we're going to, but just to highlight, delta H's arrowhead changes direction whether it's exothermic or endothermic. In this case, it is an endothermic reaction, so the arrow goes up. And there you go, nice and straightforward, and it's a nice easy 3 marks to get us going with on this question. So here we go, 4 marks for this. Okay, this is what I mean, 4 marks for a Le Chatelier question, and again, it's a very, very nice question. So explain how the principle can be used to predict the conditions of pressure and temperature for a maximum yield in the equilibrium 22.1. So let's go back up to the equilibrium. Now, we're told the delta H, very important. Delta H is endothermic, so that means that going across the top is endothermic. So left to right is endothermic, right to left is exothermic. Now, if we want to maximize the yield of product, we need to move equilibrium to the right-hand side. Therefore, in order to move to the endothermic side, we'll need to do the opposite of endothermic. So that means the temperature is going to have to go up. So the first part of the answer, okay, we increase T, increase temperature. That gives you 1 mark, by the way. That's the first mark. And the second mark for temperature is explaining it. And all you got to say to explain it is because forwards reaction, RXM reaction, is endothermic. That's it. Okay, 2 marks. Okay, increased temperature because the forwards reaction is endothermic. Okay, that's 2 marks already. Bearing in mind, by the way, they've given you like 8 lines to write on. That gets you 2 marks. Next one then, it needs you to talk about pressure. So we've done temperature, let's just tick that off. pressure next. So let's go back up to the equation. So for pressure then, we need to count the number of gaseous moles on each side. So on the left-hand side, we've got 1 mole of CH4, 1 mole of H2O, so 2 moles of gas. On the right-hand side, 3 moles of hydrogen, 1 mole of CO, so 4 moles of gas. So we've got more on the right than we have on the left. So we need to make it go to the side with more moles of gas. Now, the way we do that, if we want to shift it to the side with the most moles of gas, we have to lower the pressure. Okay, increasing the pressure forces it to the side with the smallest amount. If you lower the pressure, it will shift to the right-hand side, the side with the higher moles of gas, to try and re-increase that pressure. So therefore, all you need to say, to explain it by the way, so lower pressure is 1 mark. To explain it, all you have to say is that the right-hand side, or the product side, has more moles of gas. And that's it, 4 marks. And you can do that in 2 lines. So a nice straightforward example there of how you don't need to write an essay to get full marks. Brevity is key. Put down the most important points and you get the marks. If the examiner's got to read an essay, you know, where you've gone on for 10 or 15 lines about everything you know about equilibrium, there's a chance that the examiner will miss your perfectly valid point. Okay, it happens. So keep it brief, keep it short and simple, and pick up those marks and make it easy for the examiner to spot where you're picking those marks up from. Lots and lots of writing. Occasionally your correct answer can get lost in the barrage of text. So short and sweet is the way I would do things. Right. Bond enthalpy calculation then. So it gives you the same equation, okay, that we had earlier. Average bond enthalpy is shown in the table. Calculate the H to H bond. So the way I would do this then is straightforward. Okay, so we need to calculate an unknown bond here. So we have CH4. Okay, it's better to draw it out here just to make sure we don't forget any bonds. Although we're probably not going to. It's good practice. Okay, H2, and there's 3 of those, and CO, and we know it's a triple bond. Now, it's already balanced. It's balanced for us. So all we need to do now is calculate the H to H bond. So remember, reactants minus products equals delta H. So R minus P equals delta H. So let's put in what we do know. We know delta H is 206. So I'll put that in at the end. So equals plus 206. Now, the product, we only know CO. So we know we know it's minus 1077. We don't know the H's and we know the other 2. So let's work out the ones that we have to do a bit of multiplication for. So we've got 1 mole of methane. So we've got 1, 2, 3, 4 C to H bonds. So 4 times 413. Plus, we've got 2 OH bonds. So 2 times 464. So those are your reactants. Now we've got to subtract the product. So minus 3x, which is our H's, which we don't know, minus 1077 equals plus 206. So let's just simplify the brackets that I've drawn. So 4 times 413. Let's add that on to 2 times 464. And we get 2580. So that means that 2580 minus 3x minus 1077 equals plus 206. Now, obviously, I want the minus x to be plus x, ideally. So I'm going to take the minus x, shove it over the other side, and at the same time, I'm going to move this plus 206 onto the other side. So that means that 2580 minus 1077 minus 206 equals 3x. So we can simplify this down quite substantially now. So 2580 minus 1077 minus 206 gives me 1297. So 1297 equals 3x, and then it's just a simple amount divided by 3. So 1297 divided by 3, and you end up with 432.3. So that is your answer, 432.3. I mean, you can round it, I suppose, 432, but I don't think it really matters. You just put the 0.3 on, doesn't really matter. Just be aware, it must be a positive number. Okay, all the numbers in the table are positive. So when you report bond energies, they have to be positive. If you do this a different way and you've got a negative answer, okay, make sure that you just convert it to positive. Okay, that's a guaranteed way to make sure you get the mark, because it has to be positive. There's no question that, there's no question or debate there. It must be positive. Otherwise, that's actually quite a nice bond enthalpy question for 3 marks. So 23 then. Chlorine is used to kill bacteria. One risk using chlorine. I'm not going to dwell on this. Okay, just learn the word toxic. Okay, whenever they ask about chlorine and risks of chlorine, it's toxic. Move on. 1 mark. Let's go. Now, equation is given. Okay, it's preparing chlorine from hydrochloric acid and manganese oxide. Not really important. The important bit is showing which element has been oxidized and which has been reduced. So what I will say is here, just assign all the oxidation numbers using the rules that you know. So remember that hydrogens are always +1 unless they're bonded to metals, and I don't see any metals here bonded to them, so that's probably correct as +1. Oxygen is always -2, unless of course it is in a peroxide or fluorine, and I don't see any of those knocking around. Elements are always 0, and the remaining ones can just be figured out fairly quickly. So if H is +1, Cl must be -1 to be neutral. If oxygen here is -2, there's 2 oxygens to make it -4, so manganese must be +4. In MnCl2, chlorine is usually -1 in a compound with a metal. So in ionic compounds, chlorine is -1, which makes manganese +2. And there you have it. Those are all the numbers. All you got to do now is look for which ones have changed. So chlorine is quite clearly gone from -1 to 0. Okay, and that's oxidation. It's lost an electron. And manganese has gone from 4 to 2, which is reduction. So in terms of writing it down, oxidation is chlorine, -1 to 0. Manganese is reduced, +4 to +2. Nice and straightforward, nice easy 2 marks. Right. Mixture of potassium perchlorate and aluminium is for fireworks. It's a reaction. Write the balanced equation. So let's pick out the key information. When the firework ignites, this reacts with aluminium to make potassium chloride and aluminium oxide. So if you pick out the information here, you'll realize they've given you all the information. So it tells you KClO4 reacts with aluminium to make KCl and Al2O3. All you've got to do now is balance it. Okay, which is easier said than done. I will agree. However, little trick we can use here. Little trick. Okay, because you may look at this and go, oh, actually, it's quite easy. And actually, when you start looking at the numbers, it can get quite complicated very quickly. However, I would focus on elements that are hard to balance. So in this case, the chlorines are already balanced, but that can't be right. And the potassium's balanced, but that can't be right. It's the aluminiums and the oxygens that are the problem. Now, you could probably put a 2 in front of the aluminium and figure it out from there. But if you put 2 in front of the aluminium, you run across the issue that the oxygens become an absolute pain, because you then can't change this value here to make more oxygen. So the oxygen becomes a problem. However, oxygen only appears in one reactant and one product. So let's find a common factor. Okay, got 3 oxygens on the right and 4 on the left. Let's find a number that both of them can go to. So 4 times 3 is 12. Okay, so I want 12 oxygens on each side. So I'm going to put 4 here, and I'm going to put 3 here. This balances the oxygens and eliminates any problems we might have. The upshot of this, of course, is that I've created 3 potassiums and 3 chlorines. That's very easily balanced by putting a 3 here. And of course, I now have 8 aluminiums, but that's not a problem. I can stick an 8 there. And it's balanced. Okay, so yes, the balancing numbers are strange. 3, 8, 3, 4 is not you're not your straightforward balancing act. However, if we think about it, balancing the oxygens is the key to the whole thing. So balance those first and the rest just falls into place. Right then. Trend in the reactivity of the halogens. This is honestly an amazing question for 5 marks. 5 marks, is it? Yes. So the student is given chlorine, bromine, iodine, and cyclohexane, and aqueous solutions of sodium chloride, sodium bromide, and sodium iodide. Plan an experiment to show the trend of the halogens. Include all observations and an ionic equation for one reaction. So first thing first then is going to be, I'd say include, what would you do? So plan the experiment basically. For the first mark, all you're going to have to write is, mix halogens with halide solutions. That's enough to get you 1 mark because that's what you'll have to do. Now, what you'll actually get then. So if you use, there's 3 reactions that are going to give you. So you can use your own knowledge here. Don't be afraid. You know that chlorine is more reactive than bromine, which is more reactive than iodine, so use it. Okay, you know if you react chlorine, so chlorine and bromine, okay, you know chlorine will displace bromine. So Cl2 plus NaBr is going to make NaCl and Br2. Nice and straightforward, yeah? And just put some balancing numbers there to make it fit. Now that's not an ionic equation, but that's what will happen. All you have to do now is think of what happens to the colour. So it tells you what the colours are in cyclohexane. So in the beginning, Cl2 is pale green, and the bromine I produce is orange. So when I add these together, I'm going to go from pale green to orange. There you go. First one done. And the same applies for chlorine and iodine. Okay, if I do chlorine and iodine, the same thing will happen. Okay, it goes from pale green, only this time instead of going to orange, it will go to violet. If I react bromine and iodine, so let's just put Br plus I, or just bromine and iodine. Again, bromine replaces iodine, therefore it will go from orange to violet. So I add pure bromine to start with, and then it turns to violet. If you add iodine, of course, you would get, nothing. If you add iodine to any of the others, you get no reaction. But that's all you need. So you see those 2 observations, pale green to orange, orange to violet. That's enough to do it. Okay, and therefore you can write the reactivity trend is Cl2 is more reactive than Br2, more reactive than I2. And to do an ionic equation, just as a final thing, just literally take the sodiums out of that equation I just wrote. So let's just say Cl2 plus Br minus, 2Br minus, goes to 2Cl minus plus Br2. Okay, the sodiums cancel because on both sides you would have 2 lots of Na plus. So if I wrote this properly, okay, before I cancelled, I'd have 2 Na plus here and 2 Na plus there, and they just cancel because they appear on both sides. So we don't need to include them. And because of that, we get this equation here, which is an ionic equation. You can do an ionic equation for any of the reactions that would take place. They're all very much the same thing. They're much of a muchness. Okay, but there's lots and lots of marking points here that's easily missed. So there is a mark just for writing the trend in reactivity. There is a mark for saying that you mix the 2 together. There are 2 marks available for the colour changes, 1 mark for the ionic equation. So 5 marks, not a great deal to write. Again, I've only jotted down my answers, but you can see how little I've wrote here to pick up those marks. And again, brevity is key when you answer these questions. Okay, stick to the point, put the key observations down. Again, tick off what you've got. All expected observations. So I've probably not put all of them down, but I've put the important ones down. Chlorine and bromine, pale green to orange. Bromine and iodine, orange to violet. Chlorine and iodine, pale green to violet. And then you could also put iodine and chlorine, no colour change, for something like that. Okay, and I've done an equation for one of the reactions, that's done as well. So nice and easy 5 marks there, nothing too complicated. Okay, right, so reaction 1 then. You've got methyl propane reacting to form compound A. It is a very, very clear and obvious electrophilic addition reaction, which of course I've now spoiled because I've said what the name of the mechanism here, but it's electrophilic addition. How do I know? I've got a double bond and I'm adding HBr. That's always a dead giveaway. HBr is going down here. I'm going to put down here electrophilic addition. Forgive my terrible handwriting. So, straightforward mechanism, as always. Make sure you put your dipoles on. This is why this works, because you have a dipole between the hydrogen and the bromine. Arrow starts from the center of the electron dense region, which is the double bond, goes to hydrogen. The hydrogen-bromine bond breaks, so from the bond to the bromine to form your intermediate. Now be careful with your intermediate because it tells you what the product should be. So it tells you that the hydrogen goes to the right-hand side. It's very important, okay? You can see what the product is, so match up your answer to what that product is. There is a mark to be lost if you don't do that. Positive charge on the carbon, Br minus is left behind with a lone pair. From the lone pair, all the negative charge straight to the positive charge, and you get your product. 4 marks. Couldn't be easier. Okay, you effectively get 1 mark per arrow and the dipole, I suppose, and then 1 mark for the name electrophilic addition. It's a very, very straightforward question, this. And remember, electrophilic addition, all of these things, all of these mechanisms are always the same thing. It's the same arrows over and over again. Nice and easy. I'm not going to dwell too much on this. It's nice and straightforward. Right, explanation of terms then, a little bit of a definition. Again, structural isomer is when you have the same molecular formula. So C4H8, for example, but a different spatial arrangement. Okay, not spatial, oh dear, what am I talking about? Not spatial arrangement. By spatial arrangement, I mean structural arrangement. Okay, different structure. I'm getting ahead of myself here. Different structural arrangement. Forget what I said about spatial, that's stereoisomers. Even I get confused after a while. After doing all these questions, I get confused myself. So, same molecular formula, different structural arrangement. Okay, so you're just moving around. So that's when you can actually physically take apart and move the atoms around. And it tells you that compound B is a structural isomer of compound A. Draw the structure for it. Well, when it reacts, what's the only thing that can be different? Well, in this reaction, the hydrogen can either go on the right-hand side or the left-hand side. In this case, it went to the right-hand side, but if it went to the left-hand side, that's a different structure because the CH3s here are different to the hydrogens. So if I swap these two over, it is a different compound. So just draw exactly what we just did, but with the hydrogen on the other side instead. No more complicated than that. And you get yourself 1 mark. Nice and straightforward. Right. Compound A then, keeping up with compound A, we're going to carry out a reflux of compound A to make alcohol C. Choose a reagent and complete the equation. So alcohol C, okay, to make the alcohol, you're going to need to replace the bromine with an OH group. Now, to replace bromine with OH, this is your straightforward nucleophilic substitution. So anything containing an OH minus, basically. So you would need NaOH or KOH or LiOH, or just OH minus would be enough. The alcohol is simply the exact same compound, but with the Br replaced, okay, because you've done a substitution reaction. And of course you would form NaBr as your product because the bromine would react with the sodium to form sodium bromide. Nice and straightforward, just hoping you can recognize a nucleophilic substitution reaction. Draw a diagram. This is where I'm going to be useless at this with this little tablet I've got. So okay, so important features to include then to make sure you've got this right. So you will need, okay, a pear-shaped or a round bottom flask. Okay, so you can label it, okay, pear-shaped flask or round bottom flask. Either is fine. You will of course need heat, so just an arrow for heat. Then you do need that for the mark, by the way. And the second point you need to get the marks is a condenser. Okay, I'm not going to draw this very well, mind you. You need a condenser coming off the top. Okay, and then you need labels for water in at the bottom and out at the top. Okay, and that's a condenser. And that's all you need. For 2 marks, that's all you need. Doesn't need to be a work of art. You don't need, this is an art class, obviously. But you do need to label water in, water out condenser, pear-shaped flask, and heat, and draw something that looks like it. This looks more like a spear, if I'm being honest, but it'll do. Okay, for what I'm doing. You should know what it looks like. Nice and straightforward. Right then, question 25 then. Scandium then, reacting with oxygen to form an oxide of scandium. They've given a method, okay, so they're heating scandium, adding oxygen to it to work out, the empirical formula. So, a couple of important things then to do here. Okay, you need to work out how much scandium you started with. So, that will be the mass of the crucible and the scandium minus the mass of the crucible. So 12.435 minus 12.165 equals 0.27, and that is the mass of scandium. The second thing you need to work out is how much oxygen you've got, and that's the difference between the second value and the third value. So mass of oxygen added is just the difference. So 12.579 minus 12.435, and that will give you 0.144. All that remains now is to work out the moles of each. So you do 0.27 over the molar mass of scandium, which is 45, 0.144 over the mass of oxygen, which is 16, gives you 6 times 10 to the minus 3, and 9 times 10 to the minus 3. If you divide by the smallest number, okay, you'll end up with essentially 1 scandium to 1.5 oxygens. Therefore, your empirical formula, the simplest whole number ratio, is scandium 2, oxygen 3. So nice and straightforward, that question. It's just basic empirical formula, picking out data from the table, knowing you're working out the mass of scandium you started with, the mass of oxygen that was added, and then working out empirical formula in the same way you would normally do. The next question then on this paper, going on from the empirical formula, we have the gas cylinder contains a volume of 9.39 decimeters cubed. So we've just underlined the numbers here just to highlight them a little bit. So gas cylinder holds 1.69 kilograms of a gas that we don't know at a set pressure and a temperature. Now, as I've mentioned before, if you see questions where you are given volume, pressure, temperature all in one big go, it is almost always ideal gas. Okay, especially AS level, there's no other reason for them to give you a pressure unless you need to use the ideal gas equation. So we know we're going to use PV equals nRT at some point. Let's see what we need to work out then. We need to work out the molar mass and identity of the gas. So to begin with, the molar mass, we need to determine the molar mass from the moles. So in terms of the values in PV equals nRT, the one you would need to work out the molar mass is the moles. So we're going to need to rearrange this equation to solve for N. So N equals PV over RT. Again, you should be familiar with how to rearrange this equation. If not, it's something that you can just learn if you're not mathematically minded. From this then, we just need to plug in our numbers, ensuring we use the correct units. And this is the biggest issue with these questions, I find. So let's start with the pressure. Now the pressure is in pascals, and that should be in pascals. So that means that we're good. We can leave that as it is. So 1.37 times 10 to the 7 goes here in the top. And we're going to multiply that by V. Now V is the volume. Now we've got 9.39 decimeters cubed. We need to convert this into meters cubed. This is the common mistake that people forget. Has to go to meters cubed, so we have to divide by 1000. And therefore it's 9.39 times 10 to the minus 3. All over, so R is a constant, 8.314, it's on your data sheet, multiplied by the temperature, which needs to be in Kelvin. So it's given in centigrade, we need to add 273 to that to get 293. Plug it onto your calculator, just be careful with getting the numbers in the calculator correctly. You should get 52.8090, etc. It's a big long number on the calculator. That's the number of moles. Now we need to work out the molar mass. So remember that molar mass equals the mass over the moles. So we simply take the mass of the cylinder, of the gas in the cylinder, so 1.69 kilograms, convert it to grams because we need to convert to grams because molar mass is measured in grams per mole, not kilograms per mole. So 1690 just times by 1000 divided by the number of moles, 52.809 blah blah blah, and you end up with 32.00207, etc. or 32. Okay, so we're just going to say it's 32. Nice and straightforward. So the molar mass is 32, and it's a gas, so we're looking for any gas that we can think of with a molar mass of 32. Now, there aren't many options if you look at the periodic table. It doesn't say it's a compound or an element, which does make it trickier. But if you try and make 32 work with numbers on the periodic table, it's actually quite difficult to make it work with your basic elements, carbon, hydrogen, oxygen, etc. So it's probably going to be something that's a common gas. It's not going to be something really obscure, okay, that you've never heard of. It's not going to be like, N2H4, which would give you 32. But who knows, do you know what N2H4 is? Probably not. Okay, so keep it simple. Think of common gases that you know, and a very, very common gas that has a molar mass of 32, something you really should just, be able to work out, I suppose, is oxygen. Okay, because one oxygen is 16, and therefore two of them are 32. So the gas is going to be oxygen. So in terms of working that out, it really is just, well, it's a guess really. You're given a molar mass of 32, you know it's a gas, therefore it's likely going to be something you've heard of. And of all the common gases you've come across at AS level, oxygen is really the only one that fits the bill. So moving on then to the final question of the paper. So organic compound E contains carbon, hydrogen and oxygen. Only that is important because it very much limits what we can put in there. It gives you a mass spectrum, gives you an infrared spectrum, and it says to analyze the information to suggest two different structures. So clearly there's not enough information here to just figure out one of them. Now, in terms of how to work these out, then there's people do things in different orders. Personally, what I would do, I would look at the mass spectrum first, but not the whole thing. I would just want to look at one bit. The bit of the mass spectrum I want to look at is the molecular ion peak. So that is the biggest peak that is furthest over to the right, because that tells us the molar mass of the compound. Now, this is at 88, so we know the molar mass of our compound must equal 88. That's useful. Okay, we don't know how many carbons, hydrogens and oxygens there are, but we know they must equal 88 at some point. Okay, now I am interested in this fragment here because that's the base peak, that's the biggest peak. But I mean, I can tell you what that is by looking at it, but as a student, you may not. I'm very experienced in this way. I know what that is just by looking at it. However, we can leave that for later. Fragment ions are the last thing you want to assign, okay, because it could be anything realistically. I've got a good guess, but I could be wrong. Assign fragment ions at the end. Look for the molar mass and then come away from it and go back to it later. Now to the infrared. Now, the infrared spectrum has a couple of peaks of interest. Okay, the first peak is this one here. Okay, at about, well, 1,700 wave numbers. Off your data sheet, this is a very clear and a very obvious peak to spot. And if you do get them, you know, you should be happy, I suppose, because it's quite an obvious assignment. It's very, very clearly a C double bond O group. Now, that's just one part of the story, because if we look at the peak at 3000, normally you would say, you know, there's a CH peak, there's always some sort of peak here. However, this is a very broad peak, and it appears between 2,500 and 3,500. And off your data sheet, a peak such as this is likely an alcohol peak, specifically from a carboxylic acid. Now that's very, very important, because that tells us one of our functional groups. There might be more, there might not be, but it's very important that we can assign that this is a very broad peak. Okay, so a CH peak would not be this broad. Okay, not at all. In fact, this little section here is probably from the CH peak overlapping. Okay, we don't need to know that, but it's normally quite short, you know, quite narrow and quite sharp. The OH is a broad peak, okay, specifically for a carboxylic acid. So I'm convinced that this is a carboxylic acid. Again, in your answer, okay, you can annotate the diagram, you can annotate the spectrum, you'll get marks for that, but there's nothing wrong with, in your answer, just putting down the basics, you know, mass spec, you know, MZ peak, whatever you want to call it. The MZ peak is at 88, therefore MR equals 88. Yeah, that'll get you a mark. From the mass spec, sometimes from the IR, you can just say, you know, you've got a peak at, you know, between about 1600. It's about 1600. I think it's about 1600. Yeah, somewhere between 1600 and 1800. Peak 1600 to 1800 is your, you know, C double bond O, and the peak somewhere between 2,500 and 3,500 is the OH for a carboxylic acid. Okay, so don't be afraid to just annotate your spectrum. Okay, as long as you write all the key information on there and it's obvious what the numbers represent and what the labels represent, you don't have to write anything here. But if you want to be cautious and ensure you get everything down, this is the key information you need. From this then we can actually work out the structure. So how do we do that, you say? So we know that the mass is 88, and we know that we have to have somewhere in our compound a carboxylic acid group. Now a carboxylic acid group, okay, if we work out how much it weighs in terms of molar mass, we've got 16 for the oxygen, another 16 is 32, 12 is 44, and 1 for hydrogen is 45. So do 88 minus 45 to work out what's left over, and we equal 43. And funnily enough, 43 is the most common fragment that we have. Okay, so this is clearly where it breaks to form that fragment of 43, but we'll get to that in a bit. We've got our carboxylic acid group. Based on what we've seen in the mass spec and the IR, there are no other functional groups that are obvious to spot. So for now, let's just assume that, you know, this is it. We only have a carboxylic acid, and the remainder of the compound is just carbon and hydrogen. If that is the case, can we think of a carbon-hydrogen chain that will get us to 43? Now, you can just keep adding it on now. Okay, so if I add a CH2, that's 14. Okay, that takes me down to 29. If I add another CH2, that takes me down to 15. And then a 15 remaining means I have a CH3 group, 12, 13, 14, 15. And therefore, my answer is going to be butanoic acid. Okay, and you can assign this peak of 43 is your 3 carbons in a row with a positive charge. This is the fragment ion that's left behind when you break that bond. So it's butanoic acid. We know that's the answer. We've worked it out based on using the mathematics. So in our answer box then, we need butanoic acid, which is nice and straightforward. However, it does say there's 2 different structures. So, and the reason for this is because there is an alternative that makes perfect sense. Because if this is our molecular formula and this is our arrangement, that's one possible arrangement. There is an alternative structural isomer of this compound that could be the answer. And we have no way of figuring out which it is because we're not given enough information. So what if, instead of having 4 carbons in a row, we have 3 carbons in a row, and we have a methyl group off one of them. So it's a branched chain instead of a straight chain. It's a structural isomer. It's the same number of carbons, hydrogens, and oxygens, but there is no possible way to distinguish between the 2. So that was a full run through then of the second half of the breadth in chemistry paper from 2021. On the whole, I think it was quite a nice paper. The last 2 questions in particular, 10 marks between them, is a significant chunk of the paper. And if you're good at ideal gas questions, it's a very, very easy 5 marks. If you're good at IR and analysis, and notice here, there's not actually a lot I wrote down. In terms of where the marks are, I mean, just to point out to you what the mark scheme actually says here, there's 1 mark for getting the molar mass, there's 1 mark for each of the assigned peaks, and 1 mark for each correct structure. Those are your 5 marks. So very little writing is needed. Okay, what I've written down here would get 5 marks. This isn't me, shortening it for the purposes of a video. That's all you'd need to write. Okay, so again, I bang on about this so often, but brevity is key. Okay, keep your answers short and to the point, and just hit those marking points as you go through. Extraneous, extra fluff that you're writing just for the sake of it isn't going to be marked. So, okay, stick to the key points. Okay, you've got the key information, pulled it out, got the correct structures, and those are your marks. And that's the case all the way through the paper. I don't write a lot when I answer these questions because you simply have to put down the correct terminology, the correct points. I don't need to write, from the infrared spectrum, I can see that there is a peak at 1,600 and ends at 1,800. I believe that this represents a C double bond O. Okay, writing all that takes too much time. This is enough. Okay, shorten down your answer. You're not talking to the examiner, you're just giving him the information he wants. Stick to that idea and you'll be fine. So yeah, nice straightforward paper. A few little tricky questions dotted here and there, but on the whole it was very, very nice. And hopefully you can see how I've arrived at all my answers as I've gone through. So in another video I'll do the depth version of this paper as a as a combined thing. So yeah, nice little paper, and that was a complete run through of the breadth paper.